maximum running torque as well also. Okay, so now we'll solve few examples on these torque equations. Then we'll move to the next topic, torque speed torque characteristics. Okay, we'll take an example. A three-phase induction motor operating on 50 hertz supply having 4 poles. Having 4 poles. A star connected rotor has a star connected rotor has 90 volts EMF induced between two slip rings at standstill on open circuit. The rotor resistance and reactance are the rotor resistance and reactance are 1.2 ohms and 4 ohms respectively. Calculate the current per phase, power factor, and starting torque when, first case, when slip rings are short circuited and second, when slip rings are connected to a star connected rheostat of 3.2 ohms per phase. So this is the statement. So the given things are frequency is 50 hertz, number of poles are 4. Okay, it is a star connected slip ring rotor. Okay, then there is a 90 volt EMF induced in the rotor between two slip rings. It means that E2 line is equals to 90 volts. Okay, we will draw a simple diagram and I will tell you how this is like. on open circuit. Okay. Why this is on open circuit? Because once the rotor is short circuit, the voltage becomes zero, current becomes maximum. So if I want to know what is the rotor induced EMF, I should be keeping the slip rings in open circuit condition only. Okay. So first I have to test the slip ring in open circuit condition to know what is the EMF induced at standstill. Okay. So when at standstill, no question of rotation, hence I can keep the rotor in open circuit condition. Okay. So if you want to know the rotor induced EMF, so rotor induced EMF is always uh, obtained at standstill condition only. Okay. No doubt it is obtained even in running condition, which is S into E2. But if you want to measure it, you have to measure at standstill condition. Okay. So that is 90 volts at standstill or at open circuit. The rotor resistance and reactance are, I can write R2 is equals to 1.2 ohms and X2 is equals to 4 ohms. Okay. Calculate the current per phase, power factor, and so what I have to find is I2 cos phi 2, okay, and TST. Okay. When at uh, slip ring short circuited, slip ring shorted, and when there is an external resistance of 3.2 ohm per phase. And there is an external resistance of 3.2 ohm per phase. Okay. Now we will draw the circuit diagram. Uh, there is nothing mentioned about the stator winding. Okay. So one thing you should remember, generally the slip ring induction motor stator is connected in star and squirrel cage induction motor is connected in delta. It is general, very general connection. If nothing is mentioned about the connection, then we have to consider this. Okay. So how a three-phase induction motor is represented uh, as a circuit symbol. Okay. So we have a three-phase stator. Because it is a slip ring motor, I take a star connected stator. So this is stator. So here we are applying V supply. How much it is given, we don't know. And we have a rotor. Okay. And to this rotor, we have a slip ring connected. So these are the three slip rings which are connected to the rotors. So uh, all that got erased. You know the statement. We'll write only the given things and we'll continue. I think today the time is not good. Okay, you have that statement. Please refer that in the video. So we have F is equals to 50, okay. P is equals to 4, star connected slip ring rotor. It has got R2 is equals to 1.2 ohms, X2 is equals to 4 ohms, then E2 line is 90 volts. That's what is given. Then I have to find out I2 cos phi 2 and TST. Okay. So when first case slip ring shorted, second R external is equals to 3.2 ohms per phase. So this is a stator supply or a stator winding. Okay, represented as supply, and we have a rotor, star connected rotor. And to the shaft there are 3 slip rings. This is a circuit symbol of induction motor. Okay, slip ring induction motor. Okay. So the 3-phase rotor winding is connected to slip ring, and the slip rings are connected to some external resistance. Okay. This is a star connected external resistance. Now in the first case, the slip rings are short circuited. It means that these 3 slip rings are short circuited on themselves without this external resistance coming in contact with the winding. So this is 3.2 ohm per phase. Okay. In the second case, this switch, okay, is suppose I have a switch here. Okay, two-way switch. If I connect this switch on the slip ring side, it will be making the rotor short circuited without adding the external resistance to the circuit. If I keep the switch on the opposite side, then these 3 connections, these 3 resistances will be connected to the rotor, okay, and these 3 resistances will be added in the rotor winding. Okay. Now I have to first find out the current power factor in TST when the rotor is short circuited. Okay. So here the voltage induced is between these 2 slip rings. Okay. So between these 2 slip rings is 90 volts. So what does this mean? It is a line voltage between 2 terminals of the star connection. Okay. But all the quantities what we take in any equation are per phase values. So therefore, I have to first take the per phase rotor voltage. Solution. Rotor EMF per phase E2 is equals to, it is 90 divided by root 3 equals to 51.96 volts. So this is my E2. Okay. So in case 1, First case, when the slip rings are short circuited. When the slip rings are shorted. Okay. So when slip rings are shorted, my R2 is equals to 1.2 ohms. My R2 is equals to 1.2 ohms. So no external resistance is added into the rotor circuit. Therefore, my Z2 rotor impedance Z2 is equals to under root R2 square plus X2 square equals to under root 1.2 square plus 4 square. Is 4.17 ohms. It is 4.17 ohms. Then, therefore, rotor current I2 is equals to rotor current I2 is equals to it is E2 by Z2. So it is 51.96 divided by Z2 is 4.17. It is 12.44 amperes. And rotor power factor cos phi 2 is equals to R2 by Z2. So that is 1.2 divided by 4.17. Is 0.287. Lagging, obviously lagging, because the nature of the circuit is inductive. Okay. Then TST is equals to K1 E2 square R2 divided by R2 square plus X2 square. And where K1 is 3 divided by 2 pi ns. Okay. So where ns is synchronous speed in RPS. Okay. And this ns is equals to okay, ns by 60. ns is equals to ns by 60. And this is 120 f upon 60p. So it is 2 into 50 divided by 4. So ns is equals to 25 rps. Okay. Then substitute that in T1 or K1 is equals to 3 divided by 2 pi into 25 equals to 0.019. It is unitless. Therefore, TST is equals to 0.019 E2 square, that is 51.96. Yeah. into R2, that is 1.2, divided by 1.2 square plus 4 square. Are you people listening to the class?
Yes.
Looking at the screen?
Yes.
Then I have written wrong values here. It is 0.019 and I have written 0.015. I think nobody is concerned about the classes.
So 12.796.
No.
3.54.
Yes.
3.52,
Yes.
3.529.
3.52.
3.53 Newton meters. 529, it is 53 Newton meters. Okay. You need not to take under root here in the denominator. Maybe that mistake you have done. Okay. This is the first case. Now second case. Okay. R external is equals to 3.2 ohms per phase. So when I am adding the external resistance to the rotor circuit, then my rotor resistance per phase will be, okay, so with R2 is equals to 1.2 plus R external per phase. So this is 1.2 plus 3.2. So this is 4.4 ohms. R2 now is 4.4 ohms. Okay. With this, now again I have to find the same three values. Therefore, Z2 is equals to under root uh, can I give a new name for this? R2, okay, it's fine. 4.4 square plus 4 square. Okay, yeah, equals to
5.94.
5.94 ohms. Next, I2 is equals to, it is E2 by Z2. So the voltage will not change because it is at open circuit. So 51.96 divided by 5.
Sir, Z2 is 4.83, sir.
Z2 is
4.833, sir.
no man. 5.94 is correct.
Yes, sir, correct.
Okay, 5.9 is correct. You please check. You just check whether you have taken 3.2 square plus 4 square. No, this is equals to 5 point, sorry, 51.96 divided by 5.94.
8.7.
8.74. So I2 is 8.74 amperes. Then cos phi 2 is equals to, it is R2 by Z2. Obviously, it will now increase. Okay. So it is 4.4 divided by 5.94. is 0.74, lagging. Okay, so observe, when the external resistance is not added in the circuit, the power factor was 0.28, now it is 0.7. Okay, so what I'm doing, the rotor is made more resistive. We have seen in the analysis that if the rotor is more resistive, the average torque per cycle will be more. So that is why we are getting increased starting torque, right? And the starting torque is directly proportional to R2, rotor resistance. More the rotor resistance I add, more the starting torque I will get. So therefore TST is equals to, okay, I will write K1, same equation, there is no change. Okay, E2 square R2 square plus X2 square. So K1 we already have 0.019 into 51.96 square into R2 is 4.4 divided by 4.4 square plus 4 square. That is 6.38 Newton meters. 6.38 Newton meters. So by adding the external resistance in the rotor circuit, I am improving the starting torque. Okay, I am increasing the starting torque. Move to next example. A 150 kilowatt 300 volt sorry 3000 volt 50 hertz 6 pole star connected induction motor has a star connected slip ring rotor with a transformation ratio of 3.6. The transformation ratio of 3.6. The rotor resistance per phase is the rotor resistance per phase is 0.1 ohms and reactance per phase is sorry not reactance and inductance per phase is 3.61 millihenries. Neglecting the stator impedance, find the starting current and starting torque find the starting current and starting torque on rated voltage with short circuited slip rings. Okay. So even if it is not mentioned with short circuited slip rings, it is understood whenever it is asked to find the torque, the rotor must be short circuited only. With a rotor open circuit, motor will not rotate because currents will not flow. Okay. Now the given things. This problem needs some special attention and you should be invoking the knowledge of your impedance transformation from primary to secondary and secondary to primary in transformers. Okay. Because here I need to find the starting current. This starting current is not the rotor current. Starting current in the sense the current drawn by the stator winding from the supply. I have the rotor quantities given. A 0.1 ohm and inductance 3.61 millihenries. And this statement I have directly taken from the textbook Thareja. And the statement is given wrongly in the textbook. They have mentioned rotor reactance per phase is 3.61 millihenries. Okay, so this is wrong. And even in the solution, the substitutions are wrong. Okay, so I have taken this example as it is. Okay, this is example 34.9. Example 34.9, there are some mistakes in this. So I have taken it as it is. Because if I give this statement in the in the internal exam, you will just copy as it is without knowing what is given. So this time I did not give the notes, so you people have copied from the textbook directly. Okay. That is helpless condition. Okay, I don't want to talk further on that. Next. Okay, so here first I need to find what is x2. So given things, I will write first one things. P out is 150 kilowatts, which as of now we don't need, and V is 3000 volts. It is obviously line voltage. Okay, F is equals to 50 hertz. Then number of poles is equals to 6. A star current slip ring with a rotor transformation ratio. Okay, with a transformation ratio. So here is 3.6. While finding the transformation ratio, what you did in transformers, transformation ratio was always rotor to stator, right? Oh, sorry, secondary to primary. In case of transformer, when you said transformation ratio, it was the ratio of secondary turns to primary turns or secondary voltage to primary voltage. But here you should keep one thing in your mind. If the transformation ratio mentioned, in some books they have taken this as transformation ratio, in some books they have taken it as turns ratio. When it is turns ratio, generally in transformer what you do, it is primary to secondary. When it is transformation ratio, it is always a ratio of secondary to primary. This is how we conventionally follow in transformers. But here, in some books they have mentioned it as turns ratio. In some books they have mentioned it as transformation ratio. Then what to take? Whether to take stator to rotor ratio or rotor to stator ratio. Now I have a stator voltage of 3000 volts. I want to find rotor voltage and I have a transformation ratio. Now how should I consider? Should I take rotor voltage by stator voltage equal to transformation ratio 3.6? If that happens, then my rotor voltage is more than stator voltage, which is not the condition practically in the induction motor. Remember one thing, in induction motor, the rotor induced EMF is always lesser than the stator induced EMF. Why? Because generally the rotor conductors or the rotor conductors per phase are lesser than the stator conductors per phase. There are various reasons for that. Okay, when we study those reasons, we'll look into that. Okay, so when it is a transformation ratio, given, though they are telling it as a transformation ratio, and if the ratio value is more than 1, if the ratio value is more than 1, then this is always rotor quantity to stator quantity. Sorry, it is always stator quantity to rotor quantity. If it is more than 1, it is stator quantity to rotor quantity. Either it may be stator turns to rotor turns or stator voltage to rotor voltage per phase. Okay, stator quantity per phase to rotor quantity per phase. So here, okay, my stator voltage per phase to rotor voltage per phase is equals to 3.6. If it is mentioned transformation ratio less than 1, then it is rotor quantity to stator quantity per phase. You should keep this thing in very much in mind, because most of the people will go wrong here only, because we have studied transformation ratio as rotor voltage to stator voltage in transformers. Suddenly when we come to induction motors, it is getting reversed. Okay, so this is equals to 1 by K, where K is the rotor to stator transformation ratio. Okay, next what is given? The rotor resistance is 1.1 ohms. R2 is 0.1 ohms, and L2 is 3.61 millihenries. It is not X2. We have to find X2. Okay, so solution. So what we have to find? We have to find IST, which is not rotor current, it is stator current, and TST, starting torque. So X2 is equals to, okay, 2 pi f L2, that is 2 pi into 50 into 3.61 milli. Sorry, it is 3.61 or, yeah, it's 3.61. So in the textbook, they have mentioned 3.61 in the statement and they have substituted 5.61 in the solution. There are a lot of typing mistakes in this textbook and solution values in this textbook. You should be careful while solving. So it is 1.13 ohms. ohms. So here IST is equals to, I can write VPH divided by Z01. What Z01 is, it is the impedance of the transformer under short circuit condition referred to primary. Okay, impedance of the transformer under short circuit condition referred to primary. Now what is Z01? Z01 is equals to under root R01 square plus X01 square. Okay, so I can write it here. Impedance of induction motor per phase referred to primary. Hope you know refer to primary, refer to secondary representation. Yes? Did you do it or not? Am I audible?
Yes, sir.
Speak up, people. Did you know this or not?
Yes,
How to represent the total transformer impedance refer to primary and refer to secondary?
Yes, sir.
So here stator is primary, rotor is secondary. So R01 is resistance per phase of motor refer to stator. Because I want to find it at the stator side. Simple. X01 is reactance per phase of motor refer to stator. Then how these are given? R01 is equals to R1 plus R2 dash, which is equals to R1 plus R2 by K square. Okay. And X01 is equals to X1 plus X2 dash, which is X1 plus X2 by K square. But here R1 and X1 are neglected because it is mentioned in the statement only and can be taken 0. Therefore, R01 is equals to R2 dash and X01 is equals to X2 dash. Okay. Therefore, R01 is equals to R2 by K square. X01 is equals to X2 by K square. And here we have 1 by K is equals to 3.6. So 3.6 is equals to 1 over K, where K is the transformation ratio. Okay. So K is equals to 1 over 3.6. Therefore, R01 is equals to R2 by 1 over 3.6 square. That is nothing but 3.6 square into R2. Okay, 3.6 square into R2. So R01 is 3.6 square into 0.1. Is 1.296. Similarly, X01 is X2 by K square, which is X2 divided by 1 by 3.6 square, or X01 is equals to 3.6 square into x2, that is 3.6 square into x2 is how much? 1.13. Okay, equals to, so x01 is equals to 14.64. Okay, is 14.64 ohms. Now I can take R2, I2, sorry, IST, not I2. So Z01 is equals to under root 1.296 square plus 14.6 square. That is 14.7 ohms. It is 14.7 ohms. So IST, the starting current, is equals to uh, voltage per phase. Okay. So VPH, what is VPH? Remember, it is a star connected induction motor. It means that the stator winding is star connected. Therefore, VPH is 3000 volts divided by root 3. It is 1732 volts. So it is 1732 divided by 14.7. So it is 117.8 2 amperes. So this is the amount of starting current drawn by the motor at the time of start. So it is, which is very high, which is a large current. So now we have to find out the starting torque. Now find starting torque, I need to have E2. Okay. To find the starting torque, I should find E2. Okay. So what is E2? Okay. E2 is equals to E2 by V1 is equals to K. Okay. So E2 is equals to what? K into V1, which is 1 by 3.6 into 3000. V1 per phase, sorry, not 3000, to 1732. So this is my E2. So 1732 divided by 3.6, 481.1 volts. Okay. Then you can find K1 is equals to 3 divided by 2 pi ns. So find synchronous speed in RPM divided by 60, you will get synchronous speed in RPS. Okay. Then substitute the value and find the starting torque. So other things we know. Okay. Other things we know. R2 we know, X2 we know. All the things you can substitute and calculate. Okay. So do that. That is your part of the work. In the next class, we will solve one more or one or two such examples on running torque also. Then we will move to torque slip characteristics.